Suppose psi of x and t equal capital A into bracket x minus x cubed e to the power negative I capital ET slash h bar. Find v of x such that the Schrödinger equation is satisfied, and we've been given a hint. Welcome to LIB Academy. Most of the times we are fond of solving the Schrödinger equation for the wave function. Psi. But what if we have the wave function and we want to calculate the potential for that particular wave function? How do we calculate that? I mean, how do we solve such a problem? Vx here is the potential that we are supposed to solve for in this problem. And the wave function that was given to us is psi of x in t equal capital A into bracket x minus x cubed e to the power negative I et slash h cross or h bar. This is a separable wave equation. So looking at this is a potential part of the energy, the wave function, the spatial, which is in terms of x, but not in terms of time. So this is the potential dependent part of the wave function, and this is the time dependent part of the wave function. So the hint that was given to us, let's put that aside before. So we are going to break the wave function into the potential part. Let's say phi of x, and then the time dependent part chi of t. So if we do that, it means now our phi of x is a whole of this thing here, a into bracket. So phi of x, the potential dependent part, equal a into bracket x minus x squared, and then our chi of x, our chi of t equal e to the power negative I a t slash h bar. So we are trying to make our work simple. That is why we are doing this. Looking at the hint that was even given to us, the hint was also something that was going to help us to solve our problem with ease. So, but let's forget about the hint for now. It's like we are already down breaking our problem down. After we are down breaking our wave function into this form, the spatial part and the time dependent part like this, we write our general time independent Schrödinger equation, which is minus h bar squared all over 2m d over dx, d squared over dx squared. So chi in phi of x plus the potential energy part v of x phi of x equal e phi of x. So this is a general time independent Schrödinger equation. So, and mostly it is written in this form. This is the Hamiltonian operator, which contains the kinetic energy part and then the potential energy part. And these are energy eigenvalue. The potential energy that we are calculating for is dependent on x only, dependent on position only. So after we break down our wave function into the spatial part, the position dependent part and the time dependent part, we now write our general time independent Schrödinger equation in terms of the wave function that we were given. So after that, we now look for where we have to simplify. For instance, we have to find the derivative of uh, the potential dependent part with respect to x, which is the second derivative. So we are going to find second derivative of psi of x. So d squared over dx squared over psi of x. And we know our psi of x should be equal to, so d over dx squared, our psi of x equal a into bracket x minus x to the power 3. This is x to the power 3. So we are going to break this down. So the first thing we do is to differentiate with respect to x and differentiate with respect to x again. So this will be equal to d over dx into bracket d over dx a into bracket x minus x cubed. So if we differentiate this term with respect to x, we differentiate only the x component, the x part. This is going to give us, if we differentiate x, it's going to give us 1. Mind you, a is still there. 1. Differentiating x cubed give us minus 3x squared. The power of x will decrease by 1. We multiply x by its power, and the power now decrease by 1. So differentiating this further, if we differentiate 1, we can't differentiate 1. We don't have any x term there again. So this term goes 0. And we want to differentiate minus 3x squared. So the power will multiply by 3, giving us minus 6. And the power of x will decrease by 1, which is x. So minus 6x. So we have a multiplying minus 6x. So breaking this down is going to give us minus 6xa. So now our d squared over dx squared psi of x is now equal to minus 6xa. So we are going to replace this one from the time independent Schrödinger equation by minus 6xa. So let's go ahead and do that. So we are going to get minus h squared over 2m. This whole term here becomes minus 6xa plus v of x psi of x. This is just psi of x, no need to differentiate it. So just write our psi of x there, which is a multiplied by x minus x cubed, then equal to e psi of x, which is a multiplied by x minus x cubed. So the next thing we want to do is to simplify it. This place here, 2 goes here 1. We have negative, getting 3 here, 3xa, which is negative 3xa. Negative multiplied by negative here will give us positive. So we are going to get positive h squared 3xa all divided by 2m plus v of x a into bracket x minus x cubed here equal a into bracket x minus x cubed. Now the next thing we want to do is to divide. Our interest is to solve for the potential energy here, which is v of x. So, and let's divide the whole term by a into bracket x minus x cubed. So a into bracket x minus x cubed, a into bracket x minus x cubed, a into bracket x minus x cubed. So this term is going to take care of that term, and this here is going to go away. Then we are left with, we've already cancelled this 2 here to give us 3, so there's no need to write 2 here again. This place becomes m. So we are going to get h cross squared over m Here we have 3. A is definitely going to take care of A there. So 3x all over x minus x3. Let me write A there. So that cancel it, you see. And this term here becomes v of x equal E. So now, let's try breaking this term down. I'm going to solve it here so that we substitute into it. So we have 3x E all over m. Let's divide it. Divided by A into bracket x minus x cubed. So to get away with the division sign, we can just multiply this by the reciprocal of this term here. So giving us 1 over A into bracket x minus x cubed. Right? So A can take care of A here. Then we are left with 3x multiplied by 1, giving us 3x all over m multiplied by x, into bracket x minus x cubed. So this is the term that we get here. We can go ahead and do cancellation for x. This x here can just cancel that here. Or better still, let's solve it this way. We can have 3x. Let's factor x out here. We have mx into bracket. After factoring 1x out, we get 1 here minus x squared. So that this x can just take care of that x. So giving us 3 over m into bracket 1 minus x squared. So but don't forget that we have h cross square here. H cross square here. I did not include it because I know definitely we are not going to get a term that might cancel it out. So there is h cross square there. But when you're doing it, try to include it so that it might not confuse you. So this whole term right here becomes that. So let's write that. So we are going to get this term here to be 3h bar squared all over m into bracket 1 minus x squared into bracket plus v of x equal e. But our interest here is to solve for vx. So solving for vx, let's this cross to the other side of the equation. So we are going to get v of x. This one crossing, we already have e there, minus 3h cross squared all over m into bracket 1 minus x squared, 1 minus x squared. So that is it for our potential energy. So if you are given the wave function and you are to look at the behavior with the potential energy in terms of that wave function, this is how you can go about it. First of all, you break the wave function down into the spatial part and the time dependent part. Then after that, you now write your general time independent Schrödinger equation. Then you add the wave function to it. If the wave function we're looking at that of psi, then we are going to get psi here. But the potential energy here is dependent on x. So we are going to focus on the x part, the spatial part, right? So that is why we introduce phi of x here, but not psi of xt, right? If we were to introduce psi of xt into this whole term, to the kinetic energy part, to the potential energy part, and to the energy value part, at the end of the day, we are not going to differentiate with respect to time. So the time component will still be there. So at the end of the day, we are definitely going to divide by e to the power minus I e t over h bar to cancel the time dependent part here, here, and here. So that is why you just focus on the potential dependent part and then make the work, simpler. So let's wrap it up again. You break your functions, then you write your time independent Schrödinger equation. Then you now work on the second derivative in terms of x here, because we are dealing with one variable. That's why we do not write partial derivative with respect to x, but total derivative. So after that, you simplify everything and make potential energy the subject. That is it for this problem. Feel free to check my quantum mechanics playlist, which is a general playlist, and then quantum mechanics exams preparation playlist. Just click on my profile picture and then go to my page, and then you see the titles over there, short video playlist. You click on playlist, you see the list of playlists that I have over there. That is it for this video. See you in my next video. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.